before we move on to the time derivatives, let us just write down second order accurate and higher order accurate derivatives, not only for the first derivative which we have already done, but also for the second derivative which appears as a diffusion term. So let us just write this down. We will not derive this, but we will leave it as an exercise for the interested student. What we have discussed so far will enable the interested student to derive these formulas. Second derivative with respect to x at point I can be written using forward differencing as 1 by delta x square 2 phi I minus 5 I plus 1 plus 4 I plus 2 minus 5 I plus 3 plus 11 by 12 delta x square fourth derivative of 5 with respect to x at I. So this is an approximation for the second derivative with respect to x at point I, represented as a forward differencing. That is why we have point I plus 1, I plus 2, I plus 3 appearing in this. This is a second derivative. So according to our convention, p is equal to 2. We have a second order accurate value. So q is equal to 2. We have one-sided differencing. So the number of points that are required are 2 plus 2, 4, and we have 4 points I plus 1, I plus 2, I plus 3. And we can also see that the negatives and the positive quotients, they cancel out each other. We have minus 1, minus 5, minus 1, that is minus 6, plus 2, plus 4, so that is plus 6, they cancel out. And what we also see here is the leading term in the truncated series, and this defines the order of accuracy of the approximation. We can get what this leading term is by expanding each of these terms around point I in terms of Taylor series expansion. We have to expand at least up to the fourth derivative. We have to retain terms up to fourth derivatives, and then multiply this expansion by 4 and this expansion by minus 5, this by minus 1, and put everything together. And when we do that, we will be able to recover this. We will not derive this in the class, but I leave it as an exercise for the interested student to do. So this is a forward differencing formula. We can also write a backward differencing formula which looks very similar to this. Plus 4 I minus 2 minus I minus 3, and the leading error is minus 11 by 12 delta x square, and here it is plus 11 by 12 delta x square. This does not make this scheme any more accurate than this scheme, because both are nominally second order accurate terms, and we expect that the contribution of this term will be small when we have small delta x. So this is a backward differencing formula. Both of these are for second derivative, and for good measure we can also write an approximation which is fourth order accurate, just to see what kind of structure it has, we can write it like this, plus 16 phi I plus 1 minus 30 phi I plus 16 phi I minus 1 minus phi I minus 2 plus delta x to the power 4 by 90 the sixth derivative of phi with respect to x evaluated at phi. So, this is, we can see it is a fourth order approximation because the leading term in the truncated series is multiplied by delta x raised to the power 4. And we can also see that we are evaluating the second derivative at point I, and in order to do this we have used points on I minus 1 and I plus 1 and I plus 2 and I minus 2. So, this is a central differencing formula which is fourth order accurate, and so that means that order of accuracy q is equal to 4 and second derivative. So, that is the number of points required for a central differencing will be p plus q minus 1, that is 5, and we can see the 5 points I plus 2, I plus 1, I minus 1 and I minus 2. We can also check the coefficients minus 30, minus 1, minus 1, so that is minus 32, plus 16, plus 16, plus 32. So, again they cancel out. What we notice is that as we go to higher order accuracy, the size of the molecule increases. So, in this particular case we are looking at I here, I plus 1, I plus 2, I minus 1 and I minus 2. So, instead of having just 3 points for a second order central differencing, we now have 5 points for a fourth order central differencing, and we can add 2 more points on either side and we can derive a sixth order accurate central differencing, the coefficients for which will be increasing in terms of magnitude. Okay. When we are dealing with stream function vorticity approach, sometimes we have to find approximations for a third derivative, and we are dealing with biharmonic equations, for example something like creeping flow over a sphere, and in such kind of conditions we will have to deal with fourth order functions, fourth order derivatives. So, let us just, for the sake of completeness, let us write down a second order accurate formula for the third derivative using central differencing minus 3 I plus 2 This is a first order accuracy. That is why we have, for a third derivative and 4 points means that we can only get first order accuracy. If you want to go for fourth order accuracy, we need to put one more point. So, that is why instead of I plus 3 we also have I plus 4 plus 14 I plus 3 minus 24 I plus 2 plus 18 phi I plus 1 minus 5 phi I plus 21 by 12 delta x square, fifth derivative with respect to x at I. So this implies second order accuracy for a third derivative involving 5 points in the forward differencing, and in a backward differencing okay, it looks very similar. 5, in this case it's each coefficient is multiplied by 5 by minus 1. So this is 5 phi minus 18 I minus 1, 24 I minus 2, 14 I minus 3 and 3 I minus 4 with resulting accuracy like this. And we can similarly write down a central differencing minus 1/4 delta x square okay. So this is a central differencing, backward differencing and forward differencing, each of second order accuracy for a third derivative. And similarly we can write for any derivative, we can write a finite difference approximation of a given order of accuracy by involving sufficient number of consecutive neighboring points either on one side or on both the sides. And using forward differencing and backward differencing we can take account of the boundary points, and using central differencing we can approximate for all the interior points, so that we can maintain, using these kind of formulas, uniform order. This must be delta x square here, uniform order of discretization or finite difference approximation for a particular derivative throughout the fluid domain. Okay, so this enables us to take any derivative and then write a corresponding finite difference approximation, and thereby taking each derivative that appears in the governing equation and substituting it with the corresponding expression, we will be able to convert a given partial differential equation at a particular point ij or ijk into a corresponding finite difference approximation involving the values of the particular variable at the grid nodes at which we want to find out the values. Okay, so in that sense we will be able to convert using systematically these finite difference approximations a given partial differential equation at a particular point into an algebraic equation. So we can do this, and we can do this even for a time derivative. even for a time derivative, when the time derivative occurs by itself, then it is no different from any space derivative that you have considered. You can write if you have a first derivative, you can write down a first order, second order, third order, whatever order of accuracy, and you can make it to the order of accuracy that you wish. But when it comes in the governing equation, then what we normally find is that we not only have the time derivatives, but we also have the space derivatives. For example, in this equation we have rate of accumulation term here, which is a time derivative, and the convection, okay, or the advection term and the diffusion term are spatial derivatives, and the source term here, it may be an algebraic expression, or it may be a differential expression, or even an integral expression. We do not know what that is. It can be different for different cases. Okay, so in the case where S phi is just an algebraic expression and we do not have either advection or diffusion, then the time derivative appears by itself and we can treat it exactly like any other derivative. But when we have other differential terms coming either from the advection term or from the diffusion term or even from the source term, then we are met with a choice. Okay, let us illustrate this with a very simple example of a one dimensional case with only a diffusion term and no source term and no advection term. So for that case we can write the equation as dou by dou t of rho phi as being equal to dou by dou x of d dou phi by dou x, and assuming d phi is constant for the sake of argument, and assuming that that is equal to d, and we can take it out and we can write this as d dou square phi by dou x square. Okay, and this is equal to okay, so this is an equation here that is a part of the governing equation for a special case of one dimensional flow without any advection. Now if we want to discretize this using the formulas that we have done here, for example we can make use of a central differencing formula here, and when we come to a time derivative, okay, let us do this space derivative at I can be represented as d times phi I plus 1 minus 2 phi I plus phi I minus 1 by delta x square. We are familiar with this. What about the time derivative? For a time derivative, just as we have an index I for x and the index j for y and k for z, we also need an index for the time step, time increment, and that is usually given the index n, and it is not given as a subscript but as a superscript. Therefore we normally write phi at x t as phi at, this is discretized as xi t n, and this is represented as phi I as a subscript and n as a superscript, where Tn, as usual, this is T naught plus n minus 1 times delta t. Okay, so just as we say that xi is x naught plus I minus 1 times delta x, and yj is y naught plus j minus 1 times delta y, we also say that Tn is T naught, that is the initial starting point, plus n minus 1 times delta t. With this notation and using the n here indicating the nth step, time step, as a superscript, we can write our forward differencing approximation for dou phi by dou t as rho phi at n plus 1 minus rho phi at n divided by delta t. Okay, so when we take this in isolation, the time derivative evaluated at the nth time step can be expressed like this, and the space derivative dou square phi by dou x square evaluated at the ith space derivative can be written like this. Now let us put these two together and then write the equation. So we have, and we can also take rho is equal to 1 and it is constant, so that we do not have to carry this all the time. So we can write this as phi n plus 1 minus phi n divided by delta t equal to d phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x square. We immediately see there is something that is missing in this. In the first case the space index is missing, and in the second case the time index is missing. Okay. So in a two-dimensional case we obviously have for phi two indices, phi I n. Okay. So when we write an approximation for this, we are not only writing at n at the nth time, but also at the ith space location, at the ith grid point. So we should put I here and I here, so that we can put I here and I here. Now what about the right hand side? So the right hand side is also evaluated at what time, because we are going from nth time step to n plus 1th time step. So we have a choice of evaluating this either at nth time step or at n plus 1. So that is at the previous value or the current value at the next time step, or somewhere in between, n plus half. Okay. So let us just look at these three possibilities and let us evaluate this at nth time step. Okay. We can also write this as d of phi plus 1 n plus 1 minus 2 phi I n plus 1 plus phi I minus 1 n plus 1 by delta x square. Or we can write this as phi I plus 1 n plus half okay. So which of them is correct? So in all the cases the accuracy of the right hand side term is second order accurate in space. Okay. But the accuracy of the time derivative is determined by this, and we can see that this is first order accurate. Okay. So the resulting approximation can be first order accurate in time and second order accurate in space. So between these two things there is no difference in the overall accuracy. Okay. But when we look at how to solve this equation, okay, then there is a vast difference between this approximation or this approximation. Let us just do that. For the time being, let us neglect this part. And let us see what we mean by solving this. We now have a two-dimensional space. This is the x direction and this is the time direction, and we are looking at phi at several points in the x direction and several points in the time direction. Okay, and for example, if you say that this is I here and this is n, this is n plus 1, this is n minus 1, I minus 1 and I plus 1 and so on. Okay, so this is the reference point here. Now, in order to solve this equation, obviously when you write an equation like this, we can see that this is an initial value problem, okay, in the sense that in order to complete specification of this problem not only requires a statement of this equation, but also the boundary conditions at the two extremes of the x, okay, so that is x equal to 0 and x equal to L, and also it requires the specification of the initial conditions. Okay, so that means that if you say that this n equal to 1 is the initial condition, this is T naught, then all the values here are specified. Not only that, the boundary conditions are specified at x equal to 0 and x equal to L for all times, and let us assume that these are constants. Okay, so it is a Dirichlet condition and it is invariant with time. So that means that in this solution domain, this value at this extreme is specified as a boundary condition for all time. So here we have the three boundaries are specified, and what we need to do is to get the points in between, and these are the points that are unknown, and we want to get the values here. Okay, now we have this equation to solve, and let us consider the first case. We can write this as phi I n plus 1 is equal to, we take this on to the other side, so that is d delta t by delta x square times phi I plus 1 n minus 2 phi I n plus phi I minus 1 n plus phi I n. So this is the formula that is available for us to calculate the value of phi I at n plus 1th time step. Now when you see what is there on the right hand side, the diffusivity is specified as part of the specification of the problem. The delta t and delta x square are specified because we are specifying the grid spacing in the time domain and the space domain, and for n equal to 1, that is at the initial condition, we know all these values. Okay, so that means that since we know all these values, now we can make use of this template and apply it to find the value here, because this is at n plus 1 at so if this is n equal to 1, this is n equal to 2, and this value will be I equal to 1 and I equal to 2. So this can be computed as I equal to 2, n equal to 2 as I plus 1, so that is 3 value, this is known, I value at nth time step, this is known, and I minus 1, this is known. So this value is now specified in terms of these three values. You can see I plus 1, I and I minus 1 are coming in this at the previous time step. So this is known, so we can compute this. Now you go to the next one here. This is specified in terms of these 3 values. So this can be computed, and we can march forward along the x axis and then get all these values all the way up to the end. Now you come here at n equal to 3. Now n equal to 3 at this particular point is specified in terms of these 3, okay, and we know these 3 because we have already computed this. So this can be computed, this can be computed, and so on like this. We can go all the way forward. So that means that using this formula here, using this template for the calculation of the value of ith spatial point at n plus 1th time, we can march forward in the x direction at a particular time step from point I to I plus 1 to I plus 2, I plus 3 all the way up to the end. And once we finish the time step calculation for all the spatial points at that particular time step, we go to the next time step and then we again compute like this. So we can march forward from point to point in the spatial direction, and then once we complete a particular row calculation, so that is for all the spatial points at a particular time, we go to the next time. So that way we can fill up all these unknowns by marching forward in the x direction, and then once this is finished we come back to the first point and then we can do like this. Okay, so we can find all the unknowns by making use of this expression at each point, and so that is the characteristic of this particular solution, where we choose to evaluate the right hand side space derivative in terms of the value at n, okay. And so we can say that the value at n plus 1 at a particular space point is expressed explicitly in terms of the values at the previous time steps. So this is called an explicit method. It is not implicit, okay. And in the explicit method, everything on the right hand side is known, and so the left hand side, which is the value that we want at a particular point, okay, in terms of space and time, can be computed explicitly and very easily in terms of the values that are already known. Now if you come to the second method here, we can write this as phi I n plus 1. We do the same thing, equal to d times delta t by delta x square times phi I plus 1 n plus 1 minus 2 phi I n plus 1 plus phi I minus 1 n plus 1 plus phi I n. Okay. Now on the left hand side we have phi I n plus 1, which is what we are looking for. On the right hand side also we have phi I n plus 1. So we can bring this onto this side, and we can write this as 1 plus 2 delta t 2 d delta t by delta x square times phi I n plus 1 is equal to d delta t by delta x square times phi I n plus 1 I plus 1 n plus 1 plus phi I minus 1 n plus 1 plus phi I n. So now this is the formula that we have to evaluate phi I at n plus 1 in the second method. In the second method, now we go back here, and these are the points that we know, and if we want to compute this value here, that is I value at n plus 1, this is given in terms of phi I n, so that is this value here, phi I plus 1 n plus 1, so that is this value here, and phi I minus 1 n plus 1, that is this value here. Okay, let us just redraw this figure. Okay, so we have I equal to 1, 2, 3, 4 and so on like this, and n equal to 1, 2, 3, 4 and so on like this. So if we consider this particular point, okay, so we know that this is given as boundary condition, this is given as initial condition, and this is given as boundary condition. So all these points are given as boundary conditions and are known to us. So if you look at this particular molecule, computational molecule, which gives us the value of this is expressed in terms of phi I n. So this is our n plus 1 and this is our I. So phi I n is this one. So it is given in terms of that value, and I minus 1 n plus 1, so that is in terms of this value, and I plus 1 n plus 1 in terms of this value. Okay, so in order to compute this, you need to know the previous time step value, which we know, and the left value and the right value. Okay, so can we march forward in time with this? It doesn't seem to be possible, because if you are marching to the right, then you know the left value but you don't know the right value. Okay, you get to this point only after computing this, but in order to compute this you need to do this. If you march from the left to the right, then you know this but you don't know this. Okay, so in that sense the value at this particular point cannot be explicitly calculated in terms of the values which are coming in this equation. Okay, so this is an implicit solution. So this is an implicit method for the evaluation of phi I at n plus 1. So in order to do this, we need to know the value of I plus 1 and I minus 1 at the n plus 1th time step, and in this particular case we know either this or this, but we don't know both of them. So in that sense you cannot simply directly independently evaluate I n plus 1, we need to couple it along with the evaluation at I plus 1 and I minus 1. So what we need to do is that we notice that the value here is expressed in terms of the previous time step, which is known, and the two neighboring values at the same time step. So we need to write down this equation for all the points which are appearing in the same time step, and then for all these things, when you put them together you get an equation something like a phi n plus 1 equal to b. Okay, and so this we solve for phi n plus 1 for all I, and after completing this, so that is we evaluate for all these points and then we go to the next step. So the next step also we write down this computation molecule for each of these, all the points appearing in that particular time step, and then we solve them simultaneously, for example using a Gauss-Seidel method. If it is found to be a convergent scheme, then we can evaluate. So we do row by row evaluation of this. So it is not possible to march forward from point to point as it is possible in the case of explicit method. We have to do a row by row calculation. In 2 dimensions and 3 dimensions there will be more number of unknowns. Okay, so we need to calculate it in a coupled way, and we may have a large system of equations which we need to solve. So, when we consider a time dependent term, okay, to recap, the time derivative itself does not pose any problem, it is just like any other derivative, but when it is combined with a spatial derivative, then we have the possibility of either doing an evaluation purely in the explicit method, which is simple, which allows us to hop from point to point in the 2-dimensional grid or the 3-dimensional grid or the 4-dimensional grid, or we can do it in an implicit way by which requires us to do a row type of evaluation at each time step in the case of 1 dimension, or a plane evaluation in the case of 2 dimensions, and a 3-dimensional matrix evaluation in the case of 3 dimensions. Okay. So, this is, we have the possibility between an explicit method which is simple and an implicit method which is much more challenging, which requires more intricate programming, because at each time you have to assemble all the constants of the matrix A and all the elements of matrix B, and then we have to assemble this matrix equation and solve it using any method that we feel is appropriate. Okay. We need to know that, we need to keep in mind that although in 1 dimensions it becomes a small thing, when you consider a 3-dimensional case where you have phi I plus 1 n plus 1 and phi j plus 1 n plus 1 and phi k plus 1 n plus 1, you can be dealing with a large matrix. So, all the difficulties that we may have with the solution of large matrix equations will appear at each time step. So, it is necessary for us to find an efficient way of solving this kind of matrix equation for a time dependent problem using the implicit method. Okay. So, the choice of whether we use an explicit method or an implicit method is very deliberate. We have to choose either the explicit or the implicit method. The question is, if the implicit method is so simple, why do an explicit method? It is a valid question. We will see in the next class that it is not as the choice is not as clear cut as that. That if we use an explicit method, we can only go in very small time steps, if it is possible at all. Okay, because we are making use of the previous values of the variables in order to estimate the space derivative here. Okay, so that means that, and if we take too large a time step, then these values might have changed in the meantime. Okay, so that means that the value that you are estimating the previous functional values may not be accurate. So, that is why we are restricted to having only small time steps, whereas in the case of the implicit method, we are making use of the current values in order to do the space derivatives. Okay. So, is the current estimate better than the old estimate? We can't say that this is more accurate, but what we know is that the current derivative based on the current estimates of the values will not be violating the conservation law. Okay, because both the left hand side and the right hand side are evaluated at the same time step, n plus 1th time step. Okay, so the kind of imbalance between one derivative which is evaluated at n plus 1 and another which is evaluated at n, okay, will not appear, and this kind of method, implicit method, can tolerate even large time steps, okay, without the solution becoming unstable. We are anticipating what we will be discussing in future classes. Okay, so from that point of view, that is why we say that the choice of whether we choose the explicit method or the implicit method is not as clear cut, and sometimes we may be forced to use an explicit method because it is so simple to program. Okay. But sometimes that may we may find that that restricts severely on the kind of delta t values that we can choose, and in such a case an implicit method will guarantee us a solution. But both are only first order accurate in time. So that means that the approximation that we are making here as forward differencing here is only first order accurate. So that means that the solution at different times is not very highly accurate. For all the space derivatives we have considered, for example, the second order accurate and fourth order accurate and fifth order accurate, like that. Okay, but for time derivatives we usually consider first order accurate or maybe second order accurate and so on. Why is that? The reason is that if you want to do higher order accurate approximations for the time derivatives, just like what we have here, we can see that a second order accurate expression for the third derivative will require 4 values. Okay, so that means that if you are writing similarly an expression for the time derivative, then we need to store the values at n plus 2, n plus 1, n. Okay, let me just put it in this one here, n plus 4, n plus 3, n plus 2, n plus 1 and n. So that means that we need to have the field values not only at n and maybe n plus 1, but also at so many points. So that means that you cannot overwrite the values that you have computed in the current time step with the previous time steps. So that means that you have to store a large amount of data in order to go from one time step to another time step. And we know that we are dealing with a large number of grid points. Typically we are we may use 1,000,000 grid points. So that means that you need to have so many more millions of values, variables that are needed to be stored. And not only that, in order to go from one time step to another time step, we need to recall these values. So these should be in an easily accessible memory on a computer, and otherwise you need to you will be spending a lot of time in retrieving the data from your core memory, and that will reduce the speed of computation. So from that point of view, we can't afford to have highly accurate schemes for the time progression, because it requires us to store large number of data which may otherwise be not necessary. Okay, so that's why we choose typically first order accurate or second order accurate schemes in time derivative, but in space derivatives we can go for more accuracy, because these values are anyway known. Okay, so this is these are the considerations that we have to keep in mind when we look at a governing equation and using a finite difference method for the discretization of this particular equation. Okay, so to summarize, when we have an equation like this, a partial differential equation, then we expand it to include all the terms that are relevant. For example, in 2 dimensions there will be 2 terms here and 2 more terms here. In 3 dimensions there will be 3 terms here and 3 terms here. So each of them is a partial derivative. Wherever we have a partial derivative, then we substitute that partial derivative with an equivalent finite difference approximation, and then we can assemble all the points together and then come up with an overall expression for a discretized form of the governing equation. Okay, so with this we will be able to convert a given partial differential equation into an approximate form of a defined accuracy or of a chosen accuracy chosen by us in terms of the derivatives involving the x direction, y direction, z direction and time direction. And when we also look at the time derivative, we also make a choice between an explicit method or an implicit method or a combination of these methods. Okay, so with making these deliberate choices, we can convert a partial differential equation into an algebraic equation which is valid, which is an approximation of the governing equation at each discrete point in time and space. And the form of this algebraic equation is such that the value of that particular variable at that particular point in time and space is expressed in terms of the neighboring points, and we need to do this approximation at all the grid nodes that are of interest to us, and then as a result of this we will be converting a single partial differential equation into one big set of algebraic equation which can be written in a matrix form like A phi equal to B. Sometimes what we have is we may have nonlinear terms, in which case it will be a set of nonlinear algebraic equations, and in order to convert it into a matrix form we may have to linearize it, and we will look at some linearization techniques or considerations in linearization, so that a given partial differential equation can be converted into something like A phi equal to B, which we can solve. So the summary is that we know now how to take a partial differential equation and convert it into A phi equal to B. So we can claim that if we know how to solve this A phi equal to B, for example using the Gauss-Seidel method which we have already introduced, we should be able to say that now we know how to solve the template equation. Unfortunately, the situation is not as straightforward and trivial as that. We have to look at more the properties of the discretized equations. Okay, so the discretized equation being like this, to see under what conditions this discretization will guarantee us a solution which is satisfactory. We will see in the next class that it is not always that we will be able to get a satisfactory solution. Many cases even the straightforward discretization which looks okay on paper may not give us a proper solution. It may give us a totally unacceptable solution. Okay, so we will look at the properties of the discretized solution. We will look at we will do some analysis to see under what conditions we can expect to get a proper solution, and therefore based on this analysis we will ultimately come up with a satisfactory way of discretizing a given partial differential equation into and converting it into a set of A phi equal to B. We only know how to solve, how to discretize a given partial differential equation. Now what we want to see is when we substitute the individual derivatives, when you replace the individual derivatives with the finite equivalent finite difference approximations, what kind of additional complications arise by which some substitutions may not give us a proper solution, and how to detect a priori even before attempting a solution, how to say a priori that this particular combination of finite difference approximations for these terms will give us a satisfactory solution. So that will be the essence of what we are going to discuss in the next classes.